All right, so thank you very much for attending today's class. This is the first in a three-part series in which I'm going to be covering our Advanced Motion Controller, or AMC for short. Now, what I'm going to be doing during the session, again with microphones, if you have questions, let me know. Otherwise, if you wouldn't mind keeping it muted, that would be great when you're not speaking. And I am recording it. We will take a break at 11 a.m. for about 10 minutes. So today I'm going to begin with an introduction to the AMC. After that, we're going to look at some initial drive commissioning, and that's important. The drive commissioning section, I monitor all of our tech support calls, and I see that there's not a lot, but quite a few people who are coming from the PLC side of the world want to begin with the PLC and go from there. And it's important to note that in order to use the AMC, the drive has to be commissioned first. So that's what we're going to do today. And we're going to finish up today with looking at the configuration menu for the AMC, which is menu 31. So I'll begin. Historically, our drives have always included the ability to perform motion control. And specifically, specifically, that was menu 13, which was our standard motion controller. Has anybody noticed that, or has anybody used menu 13 for anything before? Yeah. You've used it. Okay, good stuff. Menu 13, it's called standard motion controller, and it's kind of confusing. You can't do positioning with menu 13. Menu 13 is more for pulse input, like gearing sort of stuff. So menu 13, provides you the ability to ratio the speed to the frequency of an external encoder. It also provides some support for common CNC profiles, such as shaft orientation and things like that. But menu 13 should be disabled when you're using the AMC. So you can disable menu 13 by going into menu 13 parameter 10. And unless you have enabled it, it's disabled by default. So we've always been able to do motion control in one form or another. The advanced motion controller now is available when using our Digitex HD or any member of the Unidrive M700 family. So, the AMC will not work for the M400 or any of our Commander drives, the M600. It has to be a Digitex HD or a Unidrive M700 family of drives. The Advanced Motion Controller is an axis and a half motion controller, which is a buzzword. And what that means, it can control the motion of a single motor, but it has the ability to use a secondary reference source, such as an encoder or virtual master, which we'll learn about, as the half axis. So that's why it's called axis and a half, where the half axis has no feedback, it's command only. The AMC is configured completely using menus 31 through 41. Nothing extra is required. Once the drive is commissioned, we're going to use menu 31 through 41 to set up the AMC. And the AMC can be selectively enabled and disabled also. So if you wanted to switch between position control and speed and torque modes, you can do that pretty easily by just turning off the AMC. The nice part about the AMC is, as opposed to our previous version, which was the APC, which was part of our application module, is that every part of the motion controller is parameterized. The APC, I don't know if anybody's used that before with our SIPT software, but the APC required some sort of obscure function calls in order to use it. So the beauty of the AMC is that it's completely parameterized. In terms of the features that the AMC supports, the motion features is it supports speed mode, which is commonly referred to as jogging. It also supports relative motion profiles. Sometimes those are referred to as incremental indexes. It supports absolute motion profiles. It also supports what's called EGB mode, which is electronic gearbox mode. That's used for gearing. It supports homing, and there are 11 homing methods built into the AMC, including home to torque reference, which I'll demonstrate. And it also supports camming, which we're going to do on Friday. So these are the features that the motion controller, the AMC, supports. This graphic that you see here is probably the best graphic that our manual people have ever produced, because it explains pretty much very clearly how the AMC works. Those of you who have used our drives before, and I trust all of you have, you know that it's menus and thousands of parameters. Well, the AMC is no different. So you see here in each one of those rectangles, there's reference to a menu. And the reason for that is because of the fact that the AMC is in fact completely parameterized. So up in the upper right corner, this is what we're going to talk about today. The general setup is done in menu 31. And then right underneath that, the control and status is menu 41. Let me do my laser pointer there. So here is menu 41. Then if we move over here, the key to the AMC is menu 34, parameter 7. That is going to determine which source over here is going to be used to create your motion profile. So right away, you see that menu 34, parameter 7, you can have menu 34, parameter 7 in stop mode. And this is a real option. If you've used our drives before, you know in speed mode, for example, very simply in speed mode, you start and stop the motor with the run switch or a not stop switch. When you're using the AMC, things are very different. With the AMC, in order to, once the AMC is enabled, we are expecting that the run signal, which is menu 6, parameter 30, is always on. It's left on when you're using the AMC. So when you want to start the AMC, you update menu 34, parameter 7 to one of these sources. When you want to stop the motor following the profile that you prescribe here in the XLD cell, you shift menu 34, parameter 7 to stop mode. So this is different than operating the drive in standard speed or torque mode. So we have stop as an input to the AMC. We also have position reference mode. So position reference mode is relative profiling and absolute profiling. So if I want to execute a motion profile, I'll configure its parameters in menu 38 for speed XL decel. The position itself is set up in menu 34. And then when I'm ready to execute the motion, I'm going to shift menu 34, parameter 7 to 1. So that's positioning mode. If I want to jog, speed mode, I'm going to set the speed reference in menu 34. The accel decel for speed mode are once again in menu 38, and I'm going to shift 3407 to a 2 to start the motor, and when I want to stop it, I'll shift it back to 0. Then we have two modes that require input from a master axis of some sort. So menu 32 is the master position axis or menu. So here we're going to configure the source for the master when I am camming and when I am gearing in EGB mode. So you need to configure menu 32 first. When I'm camming involves a table which is set up in menu 36, and then the cam itself is controlled in menu 35. So I would shift 3407 to 3 to run the profile that I've set up in my cam table. If I just want to follow the speed or the frequency of the master, I'll shift 3407 to electronic gearbox mode right there. And then finally, if I want to home the system, I'll choose my home type using menu 40. My home speed is also in menu 40. My home acceleration and deceleration are here in menu 38. And when I want to home the system, I'm going to shift 3407 to homing, which is 5. So I determine the input for the AMC from one of these sources using menu 34 parameter 7 after I've already set up my user unit scaling in menu 31. So let's take position reference as an example. When 3407 is set to a position reference, the position is going to be plugged into menu 34, but the motion profile, the acceleration, deceleration, and speed are all set up in menu 38. This is a single motion profiler. We don't have the ability, to easily do compound profiles, which means doing a motion on top of a motion, which some of our earlier motion controllers were able to do. Here, there is a single profile generator. So if I want to change the position, I'll need to update the position in menu 34. If I want to change the speed, accel decel, I do that here in menu 38, and then I shift 3407 there to execute the move. So menu 38 is, as it says, the profile generator. The output of the profile generator, there's a velocity feed forward that is sent here to the summation. There's also a position reference in user units, which is set here. Then the motor position is in menu 33. So the position of the motor in menu 33 is summed with the command position, which is generated in menu 38. The net result is position error, and then the position error is fed into the position loop, which is menu 39, to correct for the position error. So this is a full-on servo now, in the sense that the base drive itself holds the current loop in menu 4. The speed loop is also held in the base drive itself in menu 3, but the position loop is in menu 39. So we have our proportional gain term here to reduce or eliminate position error. Then the output is summed with the feed forward to produce what's called the hard speed reference. If you've used our drives before, this is not a new parameter. The hard speed reference bypasses the ramping structure that's normally in menu 2 in our drives. So in a nutshell, that is how the AMC works. Does anybody have any questions about that? All right. Now, as you've seen, if I flip back one, we have, can I operate the AMC from the keypad on the drive? Well, sure. Is that a practical thing to do? No. So for all intents and purposes, you're going to need an external controller of some type to provide sequencing of the AMC. The easiest thing to think of is, well, how am I going to switch between these modes? What's going to do that? So there's a couple different options here. I prefer to use our MCI 200 or 210, our machine control module, to do this. But then that's what this graphic looks like here. But you could also use the onboard program, which is done with Machine Control Studio. So this is our PLC, as it were. So as you can see, we have the sequencer here accessing the AMC, which is in turn controlling the drive and motor. We can then interface to the drive and the AMC using some sort of an HMI. The last part of this training session, that's exactly what I'm going to do, is what you see right here. I'm going to develop a program for our MCI 210. I'm then going to use our MCH touchscreen HMI to manipulate the program, and then, of course, in the end, the AMC itself. So that's option one. Otherwise, you can use an IPC or a traditional PLC. If it's an Allen Bradley PLC, you can use the Ethernet IP interface on our drives to manipulate the AMC. We also have a plugin for Connect software called PLC Controlled Motion, which makes the setup of the AMC a lot easier. And there's a set of custom function blocks then, which can be imported into your Studio 5000 program. So the work of manipulating manually the AMC becomes a lot easier using that method. So we have PLC controlled motion for Rockwell PLCs. We also have it for Siemens PLCs. Same kind of thing. But in the end, you're going to need something to do the sequencing. And again, as I mentioned, I'm going to be using our MCI 210 module for that. Now, prior to getting into the AMC, we're going to commission the drive first. And specifically, we're going to commission the drive for speed mode. So I'm just going to set the drive up from scratch. I've got a drive here that I have set to factory defaults. And I am just going to configure this drive, commission this drive now, to operate in speed mode, preset speed mode to be exact. But here's the steps I'm going to follow. And this is kind of the rule of thumb for any kind of commissioning. You always begin with the motor data first. Motor and encoder, excuse me, we have to get that set up correctly first. Once that is entered correctly, then we perform a rotating auto-tune. Now there's been a lot of historically there's been a lot of people who skip this step. The reason for that being that you need to uncouple the motor from whatever it's connected to. Oftentimes that's not real convenient, but it must be done. There is an alternative to doing a rotating auto-tune with a permanent magnet motor. What we're trying to do here is to get the encoder phase angle. There is an alternative method where you don't need to uncouple the motor, but I'm not going to get into that in this course here. So we're going to do a rotating auto-tune. And I'm also going to add a step here. Once I've done a rotating auto-tune, in order to optimize the speed loop in the drive, I'm also going to do a inertia test. Because in order to optimize the speed loop, ideally the drive will know what the load inertia is. And there's an automatic means of calculating the load inertia in menu 5. And I'll show you how to do that. So I'm going to add a step in between there. Then we're just going to set up the I/O for whatever we're doing. In my case, I'm just going to set the home sensor up and the run forward signal, and I'm going to clear the rest of the I/O so I could use it as general purpose. Then I'm going to show you how to tune the speed loop gains. Again, a lot of people make the mistake of assuming, okay, well, this is just plug and play and off we go. Well, no. I mean, sometimes you can get away with it. I mean, sometimes you'll get okay performance without messing with the speed loop gains. But for best results and optimum performance, you do need to go into menu 3. So I'm going to show you how to do that. And then we're going to end today by going through menu 31 in the AMC to set up user unit scaling. Sound good? Does anybody have any questions? Alrighty then. So, first things first, drive commissioning. Now I'm using a Unidrive M700 demo stand. How many of you guys have demos? Is anybody following along on a demo out there? Ian? Okay, great. Anybody else? Okay. Well, if you don't have a demo, you can just follow along, without being connected, and that's fine too. So I'm going to go through these steps: motor data, feedback data. This is often overlooked, and for good reason, because we don't make a big deal out of it unless you happen to read the motor installation manual. But when you're using permanent magnet motors in servo mode, the switching frequency should ideally be set to 12 kilohertz. So I'm going to do that. Another thing that's easily overlooked is the ramp type. So when I'm using a permanent magnet motor in servo mode, I'm going to set the ramp type to fast, and then I'm going to perform my tunes, and then adjust the I/O. All right. So on the demo stand, this is the motor model number that I'm using. The only thing I care about are these 2 letters right here. These 2 letters determine the feedback device which is mounted to my motor. So I'm going to switch over to Connect software now and go through starting a new project and entering my motor and encoder data. So let me switch here. To Connect. And I have defaulted my drive right now. And Ian, if you've got a demo there, you'll know you did it right if it says trip thermistor.4. And that's to be expected when you have an NDAT encoder on the motor. So I'm going to begin by starting a new project from Network Scan. So I'll start up here. And I'm going to scan the Ethernet network right here. And there it goes. Okay, well, here we go. Now, because I'm working with a drive that's defaulted, this drive does not have a static IP address, right? And it tells you, okay, there's something out there, but it doesn't match the subnet that my computer's set up for. So that's because the default communication for Ethernet is to use DHCP. So I need to fix this right off the bat. So I'm going to click Configure. And I'm going to assign a static IP address to my drive now. Now, the IP address that I choose must be on the same subnetwork that my computer is, or I won't be able to talk to it. So I've got my network card in my computer set to a subnetwork of 192.168.1, which is terrible, but that's what most people use. And then I'm just going to change the IP address of the drive. And I'm going to change that to 100. And you can see that the software will automatically check to make sure that there aren't any other devices on that subnetwork with the same IP address. Subnet mask is here. That's not critical. The gateway is also not critical unless you are going to be connecting or accessing this drive over the internet, in which case gateway would be critical. But in today's setup, and for most cases, you aren't doing that. So I'm going to click Apply now. And there's my drive. So I'm going to say New Project with selected drives. And that's important to note too. You know, if I had 20 drives out here, they'd all show up. So I just have one. So there we go. Now we're looking at Connect. Now, I don't know if you've run into this before, but what I'm going to show you right now is, believe it or not, really important. Because I set the static IP address using Connect software here, the first thing I'm going to do is upload from the drive. Why do I do that? Connect, because I'm not online, I'm not online right now. So Connect, if I were to have looked at the Ethernet settings in Connect, it would have still shown DHCP. And had I not uploaded from the drive, and the first time I downloaded to it, it would lose the IP address because I didn't save the settings that I did using Connect software first. So now we're okay. Now we've got the IP address. If I look here, right, DHCP is turned off. There's my static IP address. So that's why you upload first. Okay. Now, another thing that's important and that I traditionally forget to do, I like to make all of my changes online. So I'm going to go online now. And then to enter my motor data, I'm going to come down here. Setup, motor and feedback setup right there. Okay, so here's motor, there's feedback. So the first thing I'm going to do is select my motor from the database of motors that's included with Connect software. So to do that, there you can see once I click in there, it shows me all the motors that are part of the database. But I'm just going to start typing the motor model number, which was 067 EDA. And my motor is a 067 EDA 300 right there. So I will choose that. Now, I don't like this button. It would imply that, oh, I'm just going to download an Autotune. Well, I'd recommend don't do that. We're going to do that manually here in a little bit. The next thing I need to do is configure my thermistor, my motor thermal detection device. As I mentioned, with the M700 demo stand and an NDAP motor, by default, it sets the encoder type to AB, just a standard incremental encoder. So that's why you see trip thermistor.4. NDAT is the only protocol that includes motor thermal information as part of the message packet that gets transmitted from the drive, or get from the motor to the drive. So I need to accommodate that by choosing my thermistor connection to be the type. First of all, the type is encoder. All right. So encoder now means that my encoder is going to, my thermal information is going to come in as part of the information that's coming in from the encoder. If I used a standard thermistor, you know, a PTY or something along those lines, I would choose that interface here. And the option is it's either coming in through the encoder cable, feedback cable, or it's coming in from an analog input. All right, so I'm going to leave all that alone. Then I'm going to come over here to feedback setup. Now, motor feedback. You're going to learn about motor feedback here in just a little bit. In fact, let me switch over and show you that. Okay. Now we'll go back. I'll show you that in a little bit. So let's choose our feedback device. So our drives have the option have a single high-density 15-pin encoder port that is divided in software into two subports, P1, port 1, and port 2. So we recommend, it doesn't have to be that way, but we recommend that your primary motor feedback be wired to the pins that constitute P1. So that's where mine is. Then I'm going to choose my feedback device. Now here is where the motor model number, in my case, was FM, right? So you click in that box, and here you notice that it's not just NDAT. There's multiple NDATs here. So that's where you have to pay attention to that code. So I'm FM, but you can see there's EM, right? There's GB, HB, there's all kinds of NDATs. So it's very important that you acknowledge what's on your motor. Yes. Oh, really? Probably not. You know, I'm using, there we go. Can you see it now? I mean, Okay, but you can't see rotary indet setup, advanced features, anything like that? Okay, yeah, this is the drop down. Yeah, that's a WebEx thing, I think. It'll show up as a shadow on the recording too, so that's kind of a thing with WebEx. So I've chosen FM. Um, and the other thing with NDAT, you see the default's 2 megabaud. Now, if you're using a motor with our single cable solution, which is the Digitex HD, and you're using a motor with a combination power and feedback in one connector, you'd want to set that to 4 megabaud. But for now, I'm just going to leave all of these at their default settings because it would work just fine. And now I'm going to send this down to the drive. Okay. Now that I've done that, you see over here, the drive is tripped. Well, it's got thermistor.4. So what I'm going to do is I'm going to reset the drive. And now my trip's gone away. So now my motor and my motor feedback are configured. This would be a fine time to save the parameters in the drive, so I'm going to do that as well. So that's step 1 of drive commissioning. All right, so let me switch back to here. There's something about absolute encoders also. So you want to make sure that if you're using an absolute encoder, it's a good idea to turn on menu 3, parameter 73. And I will show you what that is here right now. So I'll go into parameters, menu 3, parameter 73. What that is absolute turns recovery enable. And if you've got the help in Connect open, it goes into pretty good detail about what that does. Essentially what it does is it allows you to, it permits the drive to read the correct position on power up, especially if the motor has been moved as it's been powered down. So you always want to use that. Now when I did that, because I changed an encoder parameter, the drive tripped again. So I'm going to reset it. And there we go. So that's a very helpful parameter. Okay, let's go back here. All right, so we got that. Now we'll go look at menu 5, parameter 18, which is the switching frequency. And as I touched on earlier, this parameter should be adjusted to 12 kilohertz when you're using a permanent magnet servo motor. The reason for that is this parameter affects how often the current loop is updated, which is in menu 4. And once again, we're going to be requiring performance out of our motor. So I want to make sure that I optimize the current loop by setting the switching frequency to the correct switching frequency. So I'm just going to jump over and make that change. Menu 5. So menu 5, parameter 18. By default, it's 6 kilohertz. So I'm going to set that to 12 now. There we go. All right. Next, I'm going to adjust ramp mode. Menu 2, parameter 4. So by default, it uses what's called standard ramps. And in a nutshell, what that does is that when you're using a standard ramp, the drive monitors the DC bus voltage, and during deceleration, if it detects that the bus voltage is rising to an unacceptable level, it will modify the desired deceleration ramp to try to avoid the drive tripping. Well, when I have a servo motor, I can't have that. I want 100 millisecond decel. I want 100 millisecond decel. So I'm going to set it to fast, but this also implies that you are using a braking resistor, or you should use a braking resistor when you have fast ramps chosen. The drive can absorb some of the high back EMF, which causes the bus voltage to rise, but not a whole lot. So practically speaking, if you've got a load with inertia, you're going to want to use fast ramps and a dB resistor. So I will switch over now and do that. So let's go to menu 2 now. And you see menu 2 parameter 4 by default is standard. So I'm going to change that to fast. Notice also, and you may or may not know this, but anytime a parameter has been changed from default, you'll see that it's highlighted with this light blue color here. So as you're going through menus and you see things in light blue, that means they've been changed from default. And while we're at it, anything in bold font is read write. Anything not bold, like this, is read only. Okay. So we've got the ramp type changed now. So the next thing I want to do is I want to do a rotating Autotune, right? And the goal here is to determine what's called the position feedback phase angle, which is menu 3, parameter 25. That is the relationship between the motor windings and the encoder. Without a proper or a correct feedback phase angle, the flux controller will not be able to accurately provide current based on load demand. The net result of that is the drive may provide excessive current, which will lead to heating in the motor and ultimately drive trips. So this parameter must be correct. Newer CT motors have the phase angle set to 0 degrees. So if you've bought a motor from us in the last year or two, they come from the factory set to 0. But nonetheless, we need to do a rotating Autotune. So I'm going to do that next. All right, so I'll go back to my dashboard. From the setup group, Autotune. And you can read through this. I'm going to choose rotating. Next. Had I not cleared all the drive trips, it would have flagged me here and not let me go any further. But it's basically saying, okay, the drive is not tripped. You're good to go. Next. So now I just follow instructions. To start the Autotune, enable the drive by closing safe torque off. So I'm going to do that. And you can see that it is running. And on my keypad here, I'll show you. And this takes about 37 seconds, roughly. There we go. So it passed the Autotune. So it says remove the drive enable. Next. And here, excuse me, is what it's measured. Most importantly, this is not a new motor, so my phase angle is 240.4. The other thing the Autotune does is it sets the gain terms for the flux controller in menu 4. So you can see that it's set proportional and integral for the gain loop, for the current loop gains. It's got the stator resistance and some other motor data here. So I'm going to save the parameters in the drive now. And there we go. So at this point, I could run my motor. So you can see it there. The other thing I'm going to do is I'm going to change, and I didn't call this out on the slide, but I'm going to change my drive mode, my velocity mode. So I'm going to come into menu 1, and rather than using analog voltage as my speed reference, I'm going to change this to preset speed, like so. And I'm going to set a preset speed of 100 RPM here. Just because, I mean, there's no technical reason I did that. It's nothing to do with AMC. It's purely for demonstration purposes. So I'll save parameters in the drive. And let's switch back here. So we got that. The next thing we're going to do is what's called an inertia measurement. Has anybody ever done that? Was anybody aware that you could do that? Okay, so we're going to learn something today. So again, the Autotune adjusts the current loop gains in menu 4, but it does nothing with the speed loop, which is in menu 3. And like I said, you know, the default gains will get you going. It'll work, but for best results, we're going to optimize them. So what I'm going to do first is measure the load inertia, and that's done in menu 5, right? So this is also important to have the ramp set to fast. If you're going to do the inertia test, make sure that you've set the ramp mode to fast before you do this. So the inertia test is like this. Now, the first thing I do is set menu 5 parameter 21, mechanical load test level. This basically sets the magnitude of the torque reference that is used during this test. So 5% is 5% of the rated torque of your motor, or of your drive and motor combination. So this test will involve the motor moving also, by the way. It's going to oscillate back and forth during this test. So I'm going to set that to 5%, and it's an iterative test, which means it might fail. You know, and if there's different trips that are pointed out, if your speed is too high, if your magnitude is too low, so it might not pass on the first pull. So I'm going to go through and do this. Then I'm going to set menu 5 parameter 12 right here to inertia 1, close the safe torque off, and run forward. And that will begin the test. Now I should tell you, and you'll probably hear this, here in this little room, this motor just has a knob on it like you saw there. But if you're hooked up to a large load inertia, there's going to be some bad noise going on in the room, and a lot of people get scared when they hear this, but it's all part of the game. So have no fear. So I'm going to switch over there now and do this. Okay, let's get over here. So I'll close that and I'll open menu 5. So I start here, mechanical load test level. I set that to 5%. And I've got my speed, my preset speed at 100. So now I come up here into inertia 1, like that. Turn on my drive enable, and I'm going to switch to, okay, you can see, okay, so I'm going to turn this on and then run. Notice it's running. So it just sends a series of torque disturbances, for lack of a better term. Here's where the bad noise comes in. You can imagine with a large inertia, this could be pretty intense. Okay, you'll know it's done. Well, first of all, the keypad will just go right back to inhibit, but in the software you can tell also, because this will just go back to none. So it successfully passed the test. I'm going to turn off my run forward and my safe torque off. And where the results are found is in menu 3, parameter 18, which is motor and load inertia. Now, yes, we are a European company, so we're using metric terms, the inertias in kilogram meter squared, as opposed to inch-pound second squared, but you can do the conversion. So let's go see what the measured motor and load inertia was for my little test here. So I'll go back to menu 3. And there you go. So now that we know what the motor and load inertia is, now I can set my speed control. I can use an automated way to tune the speed loop, which is what this is. So I'm going to change this from disabled now. And you can see here's all the options. Most often you're going to use standard or high. I'm going to use high performance, and you see when I do that, here's my proportional and integral terms. They too are updated based on the calculations that were measured during the inertia test. So now the speed loop is ideally optimized, and I use that term on purpose, ideally. It may not be perfect, but it's at least in the ballpark. So it's 11. I think we should take a break here for 10 minutes. Does anybody have any questions? Mm-hmm. Yes, except for the switch frequency. Right. Okay, all right, because you know on noise, correct? Yeah, okay. So yeah, other than that, yes. Right, you're using a closed loop vector mode, RFCA with feedback, I would guess, so. Oh yeah, right. So, okay, great. Yep. Any other questions? All right then. Well, let's take a 10-minute break, and we'll come back in 10 minutes. And I'll pick up again. So where we left off, I had done the inertial test, and I had enabled the automated gain controls in menu 3, speed loop gain controls in menu 3. So I don't know if you're aware, but we have a software oscilloscope called CT scope. So to test to see what the results are, you would use CT scope. So I'll give you a brief demonstration of that. Let me switch over here. Okay. So here is CT scope. Now I've got two channels set up here. Channel 1 is the speed reference, which is menu 3, parameter 1. Channel 2 is speed feedback, right? So I'll enable my drive now. So as you can see, I could probably up my integral term a little bit here to compensate for some of this ringing while I'm at speed. But if you look here, accel and decel are pretty good. You know, they could probably stand a little bit of tweaking, but that's pretty good performance. I'll go back and I will adjust the integral term a bit. See if we can get rid of some of that ringing. So that is menu 3, parameter 11. And I'll just bump that up to 1.5 from 1.1. Yeah, well, that's another thing to note too. If you're using the automatic gain settings, it won't let you manually adjust those terms, right? So if I have 317 set to something other than disabled, I could freely go in and adjust these things. But once it's set to high performance, it won't let me make those adjustments manually. So I'm just going to leave those alone. That's pretty good. We'll just leave it at that. When we start positioning, we'll see what happens there, but in my mind, that's fine. Okay. All right. So next it's I/O. The last thing we're going to do here is I/O. And all I'm going to do is exactly what you see here. I am going to be demonstrating homing at some point tomorrow. So I want to make sure that my home sensor, my home switch, is connected to a terminal on the drive. So I'm going to assign terminal 25 to be my home sensor. And then, as I mentioned earlier, when you're using the AMC, once it's been enabled, menu 6 parameter 30 should be left on at all times. Now you certainly want to be aware of that if you are ever going to turn off the AMC and switch back to sort of normal speed torque mode. Because if you leave run forward on and you're in speed or torque control, well, guess what? The motor's going to run. But during AMC, I'm attaching it to a switch, you know, but during AMC, I'm just going to leave this on. So let me switch back over to connect now, and then let's look at the I/O. So the I/O, digital I/O, is in menu 8, right there. So I'm going to change terminal 25. I'm going to double click, and that's going to become menu 40, parameter 12, which is the AMC home switch that you see. Run forward, I'm going to leave that on terminal 26, but I'm going to clear the rest of these things. Just do that by typing a 0. There we go. So the only thing I'm going to use is run forward and my home switch. Now, because I've made a change to the assignments in menu 8, I need to reset the drive. Otherwise, my assignments would not take effect. So I reset the drive, save the parameters in the drive. So now my I/O is ready for the AMC. All right. Another thing to consider is the onboard user program. This is our onboard PLC program. By default, it's set to run. So menu 11, parameter 47, by default is set to run, which means if there is a program, an actual PLC program in the memory space, it would be running. And it does take priority over anything else we do. So to avoid interference, I'm going to go in and I am going to stop that by turning off menu 11, parameter 47. So I'll come in here. There it is. And as you can see, it's run. Now, it would not have affected anything in my case anyway, because if you look at menu 1148, it says the status is there's no program. But just out of force, just a habit, I'm going to say stop. Save parameters in the drive again. All right. So the drive at this point is now commissioned. It's ready for the AMC. So the next thing we're going to look at today is menu 31, which is the general setup of the AMC. So menu 31 is used to configure basic parameters, and most importantly, menu 31 parameter 6 through parameter 9. These parameters are going to be used to scale the raw encoder pulses coming from your motor encoder into user distance units, which we call UUs, which is not a very glamorous name, but that's how they refer to them, user units. So before we go there, though, you should probably understand how encoders work with our drives. So as I touched earlier today, the 700, the Digitax, has a 15-pin high resolution or high density encoder connector divided into two ports, virtual ports, port P1 and port P2. And again, P1 is where we'd prefer that you connect your primary motor feedback, but you don't have to. So the AMC defines the position of the motor using a normalized value that is derived from these three parameters. Menu 3, parameter 28, menu 3, parameter 29, menu 3, parameter 30. These are 16-bit registers. So we have a total of 48 bits that are used as part of the normalization algorithm. Menu 3, parameter 28 is the turns counter. 29 is the position within a turn. 30 is the position, the find position within a count. So it's a very high resolution system. Why do we do that? We do that to provide enough resolution for the speed loop, regardless of the encoder that you're using. Now the AMC can't read position from these three registers. It can't read and interpolate what motor position is just by looking at these three things. So we employ what's called a normalization algorithm to create a single signed 32-bit position value for the AMC. And that is based on menu 3 parameter 58, which is P1 normalized position. So I'll switch back and show you that now. So menu 3, parameter 58. There it is. So this number right here represents the actual position of the motor. So if I were to run it, you see it changes. So up here are the three registers, right? So there's my turns counter, 109 turns. There's my position within a turn. There is my position within a count. So rather than looking at these individually, the AMC, not we, the AMC looks at this value here. Now, going along with that, excuse me, parameter 357, which is the normalization turns, determines how many bits of the turns counter. So again, it's a 16-bit turn counter, right? So if I were to do the math on that, 2 to the 16th would provide me with 65,536 counts per one revolution of the encoder, regardless of what the encoder line density happens to be. Most absolute encoders are 12-bit, which means that the turns counter is set to 12, which means that the absolute position will roll over after 4,096 turns. And a lot of people don't realize that. Now, there's nothing negative. The drive will compensate for that rollover, but I've had instances where people weren't aware of that and kind of got themselves into a bind there. So we use this normalization system to provide high-resolution feedback for the speed loop in our drives. Now, 65,536 counts per encoder turn is pretty good. That's pretty good resolution. However, you can make it better. And you do that by decreasing the turns counter bits in menu 3, parameter 57. So again, most absolute encoders are 12 bits. So it'll count to 4096 before I'm rolling over. And the positional resolution will be increased now from 2 to the 16th to 2 to the 20th. So I use those remaining 4 bits of my turns counter as part of the position counter now. And now instead of 65,536, I can increase the resolution to 1,048,576,000. So that's and there are applications that do require things like this. For the vast majority of them, leaving it alone is fine. But know that you can change that if you would like to. Yes. Yeah, no problem. Correct. Right. Correct. Yep. When you reduce the turns counter, you add by 4, because normally this is 16, right? So you take the 4 that you aren't using there and you add it to the position counter in 329. I think we're the only ones that do this. I've done motion control for a long time. I've never seen anybody else do anything like this, but that is how it works, and that tends to be a little confusing. But that is how that encoder feedback system works with our drives. Right? So the AMC now, it reads the P1 normalized position, and then it multiplies that value, whatever it is, by the user unit scaling that we're going to establish in menu 31. And we're going to be talking about this next. Right? I'm going to skip over this. This talks about parameter 3106 and 3107. That is the user unit ratio for a rotary application. And I'm going to go through all this. But what this slide shows is the user unit ratio. And to get that, you divide what you have in 3106 by 65.5. You divide the two. 3106 is 360,000 in my example. I left my turns counter at 16. So at 65.536 counts per rev. So I get this user unit ratio here. And if I wanted to check what the position was, I would multiply the value in 358 by this turns ratio. Then I would go to menu 33, parameter 4. That's the motor position in user units. So this just kind of walks through how do I get from the normalized position in 358 to the user unit position, which is in menu 33, parameter 4. So we're going to talk about scaling now. So here is menu 31. And I'm going to go through these parameters now. So if you do have a demo, you want to turn on these two parameters. Right? The first one is 3101, which is AMC select. When you turn that on, it flags the drive to send the output of the AMC to the hard speed reference. So we are selecting the speed reference for the drive to come from the AMC now. 4101 will actually enable and disable the AMC. Right, so I'm going to go and I'm going to change those two parameters now. So I'll close this. Menu 31. On. Oops, I'll get to that. On. And then there's 41. So 4101. On. Right? So the AMC is now enabled. Now menu 31 parameter 2 and 3, your choices there are going to depend on what kind of an encoder you're using on your primary motor feedback. So if you're using an absolute encoder, like I am, I'm going to turn on 3102. If you're using an incremental encoder, like a standard quadrature encoder, I would leave 3102 off and turn 3103 on. So that's as simple as that. Am I using an absolute encoder or an incremental encoder? So in my case, I'm using absolute. So I'm going to go back now. And I'm going to change that. All right. Now, to show you this, I'm going to turn my drive on. You can probably hear that. Now I'm going to turn the run signal on. The motor's not moving, right? That's what we want to see. My keypad says run. The motor's not moving. The reason it's not moving is because, again, menu 34, parameter 7. It's in stop mode right now. So this is exactly what we want to see. Now what I'm going to do is I'm going to turn off my drive enable, but I'm going to leave the run on. Because again, when we're using the AMC, the run must be true. So you can do that programmatically also, which is of course what you do if you're using the onboard program or actually any PLC. All right. All right, let's go back here. There we go. All right. So when enabled, the AMC will keep track of the normalized position at all times, right? So when disabled, the slave position will always be set to 0 when 4101 is first activated. So that's the enable, disable the AMC. So unless I'm using one of these reset modes, it's always going to start at 0. And then again, I would use this if I were using an incremental encoder, right? A thing to keep in mind is the position loop integrators are always clamped to the feedback position when the AMC is disabled, right? So the last thing we'd want to do is, go out and run the drive in speed mode, then turn on the AMC only to have a huge value, turn on the position loop when I turn on the AMC. If we didn't do this, there'd be a huge following error value and the motor would just take off and run until all that following error is run out. So this is handled automatically for you in the background. Now we come to UUs, user units. All right. So this graphic down here shows you how user units are derived. So the AMC does not use labels for user units. They are just UUs, period. And it's up to you to apply a label with an HMI or whatever you're going to do. But the drive works in terms of user units. And it works like this. Again, the AMC reads the normalized position of the motor. Then it multiplies that value by what's called the slave ratio. And that is determined by the values that you set in 3106 and 3107. So the output of that is the desired position in user units, flows into menu 39, which is the position control loop, and it's summed with a speed feed forward term to produce an output ratio. So what we do here is we take motor position, utilize your desired user unit ratio. That becomes the command position here. But then the output is converted back to pulses and then fed into the AMC output speed. So we take input in user units, convert it back to raw encoder pulses, and menu 31 parameter 8 and 31 parameter 9, those are simply the inverse of whatever the ratio is here. And I'm going to show you examples of this now. So there's actually parameter 3104 and 3105 in menu 31 for a master axis, and it works the same way. So when we're talking about gearing on Friday and camming, I'll be showing you this again. But for now, we're going to focus on the motor. So the distance unit ratio is defined as this. Menu 31, parameter 6, is the quantity of user distance units. Degrees, inches, millimeters, furlongs, whatever you're doing. Just a quantity of distance units per 3107 is the positional resolution that you defined with P1 normalization turns. So unless you've changed it to a higher resolution, it's going to be fixed at 65,536. So it's the quantity of user distance units per 65,536 counts. Now on my little demo stand, we're going to simulate our rotary application. So to configure the user unit ratio, one motor revolution is 360 degrees. And unless something's changed, that's what I'm going to do. So 360 is what I want in 3106. Now the drive will only accept integer numbers, and that is very important to understand. The drive does not label them as degrees. It's assumed to be degrees based on my entry. So the value for 3107, of course, is going to depend on how you set normalization turns, but it's going to be left at 65,536. So let's go in and look at that. I'm going to go back to Connect now. And here we go. So here's the two parameters that allow you to set user distant units for a master axis. And here are the ones I'm concerned about right now. Now I'm going to put in 360 here. And I'm going to put in 65536 here. And right now, one motor turn is 360 degrees. Well, what you don't see here is that using this ratio, while it'll work just fine, it's going to limit me to position commands of whole degrees only. In other words, there's no place for decimal points here, fractions of a degree. This ratio will permit me to work in whole degrees only. So what I'm going to do, and I'll go through this again when I show you my spreadsheet, but what I'm going to do is I'm going to provide 3 decimal places for resolution, position resolution. So to do that, that number is changed from 360 to 360,000. 1, 2, 3. So now I can have a distance integrant. I can have a distance down to 0.001 degrees, given this ratio right here. These numbers must be integer. So that leads to some interesting things, and I'm going to show you that now. You all know, I remember my days working with machine builders when I was a machine builder guy. You know, the electrical guys would get it after the mechanical guys do, and they'd put in like 7.3 to 1 gear reduction ratio or something weird like that, and you'd end up with just a mess, but we'll talk about that more in a little bit. So here's an example. I have a motor connected to a gearbox with a 10 to 1 ratio, feeding a lead screw with a 1/4 inch pitch. So what do I do for that? One motor revolution is 0.025 inches. Well, I can't enter 0.025. These numbers must be integer numbers. So there's a couple different ways to take care of this. The first one is to work in terms of whole inches. So if I wanted to work in terms of whole inches, I would say 1 inch is 40 motor turns, given this relationship here. So in Connect, I would set 3106 to 1000, and again, providing me with 3 decimal places of resolution. But I'd have to adjust this to compensate for the 40 motor turns. So 40 times this is this. So my 3106 is 1000, 3107 is 2,621,440 counts. That would work fine. It doesn't change the fact that one motor rev is still 0.025 inches. It's just fitting that relationship into an integer setting for these 2 parameters. So that's one option. The other one is to set 3106 to just 25 and then add a 0 to 3107. So now it takes 10 turns. There's my 10 turns for 0.25 counts. So that would also work. I would probably go this way if it were me, but in either case, it will work just fine. Now, the maximum value that I can have for 3106 or 3107 is 2 to the 31st, which is a very large number. So you can have some pretty big numbers in these ratios. So that's a linear example with a ball screw. Now here's another one. This kind of touches on what I was just talking about. Now I've got a belt and pulley. Well, all right. So the mechanical guys picked out the right, nice, it's 8-inch diameter, 3-inch diameter. Well, the motion people don't care about diameter. We care about circumference. And in this example, now I have a repeating decimal in my gear ratio, 2.666 to 1. That is terrible for positioning applications because it will result in what's called cumulative position error over time. So here I've got the circumferences worked out, right? The gear ratio doesn't change, but I'm using inches for my user units label, and this is what I end up with. All right, if I were to divide those two, there are 9.4483 inches per turn of the drive gear. So to compensate for that, I add as many zeros as possible to 3106 and 3107 to minimize the effect of rounding errors. Right? So if I had no decimal places and I ran this one time, I turned this one time, the controller would throw out 0.4483 inches. And you can see if I moved it again, well, now I'm off by almost an inch. If I moved it again, now I'm off by over an inch. So you add zeros to this ratio to try to compensate or use as many of those repeating decimals as you can. It's not going to fix it completely, but it will minimize the effect of the cumulative position error over time. Now, to make this easier, I have a spreadsheet that I can make available to you. I don't know if you have this or not, but it's called the AMC calculator. And I think I can send it to anybody who's interested right through the meeting here. If you don't have this, otherwise you can just send me an email and I will be happy to send it to you. But what it is it just makes life easier for these scaling, for doing the user unit scaling. So, we're going to use rotary units here. So we're going to be sticking with 360,000 and 65,536. Now what I need to do before going any further is I'm going to go back to connect. Right, so here I am. So like I mentioned earlier, that's my user units. I have 360.000 degrees per one turn of the motor, but I have to put the inverse of this now so that the speed command is correct. So this is just going to be 65,536. And this is going to be 360,000. That's it. There's nothing magic about that. It's sure, yeah, go ahead. Yes. Oh, oh, sure. I mean, if you have a PLC or you have a controller that can do that, or an HMI or whatever, sure, you can do that. No, 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 no. The drive will never do that. No. Yep, and in which case you would have to update these parameters accordingly to whatever they need to be. Traditionally, I mean, in a motion control system, you've got them, you're controlling one motor, which is connected to a mechanical device of some sort, and that's not going to change. So, I mean, the relationship between the motor and the load doesn't change often. I mean, it's not, of course, you can do that. But yeah, you'd need to manually go in and update these things if that were the case. Okay? Sure. Mm-hmm. In this case, nothing. There are some things that do require, some parameters that require a reset before they take effect. And one of those parameters is the digital I/O. All right, that's one thing. There's nothing in the AMC that's going to require a reset. All right, it's just mainly to do with the base drive settings and specifically the I/O. That's just kind of this is the way it's been. But the AMC, you just want to save parameters in the drive once you've got them where you want. Oh. Yeah, yeah, it doesn't hurt. It won't hurt a thing. Yeah, it's not. I get in the habit of doing that, and there's another reason for that too. It's some, like if, for example, if I were to try to change I don't know, if I were to try to go in and change um, a value in the sequencer here, menu 6, if I just hit the enter button, which you might assume, if I'm using the keypad, if I hit the enter button, you would assume that that's fine. Well, no. So Really, the reset comes in more when you're using the keypad. And I always hit the reset and the enter when I'm using the keypad. But when you're using the software here, the only thing you have to watch out for is menu 8, right? And along those same lines, just kind of general drive stuff, there are some parameters which you can't change with the safe torque off on and the run on either. You know, like the last thing you'd want to do is go in and try to change motor settings while it's enabled. It just won't take, right? Okay. Yep. Right, so here's my user unit scaling. All right. Now, when we get Friday, I'm going to be doing a linear example when we get to gearing and camming. And again, if you want a copy of the spreadsheet, send me an email, and I will very happily send that to you. So back to menu 31, with a rotary application like ours, or our example we're doing today, the position counter within the AMC will roll back to 0 whenever the AMC slave position exceeds whatever you enter into menu 31 parameter 10. So, you know, as with any other application, rotary application, if I wanted it to roll back to 0 here, instead of going to 361, 362, 720, blah, 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 I would put a rollover value in menu 31 parameter 10. So I'll go look at that. Right, so if I wanted the position counter to roll over at 360, I would put 360,000 here, like that. Now the position counter is going to roll back to 0 as soon as it crosses this boundary. And there are applications which utilize that or which require that, so that's a good feature to have. So that's menu 31, parameter 10. Menu 31, parameter 12 defines the rate at which the AMC is updated, right? So this comes right out of the help. So unless your application satisfies one or more of these, excuse me, in the table, set your AMC update rate to 1 millisecond. So let's go back and do that. So there it is, menu 31, parameter 12. So I'm going to set it to 1 millisecond, like so. All right. Menu 31, parameter 14 is AMC speed mode enable. You should use this, you should turn this on to prevent an unwanted speed bump when the AMC profiler is enabled and switching between any of the relative, absolute, and speed modes. So there might be a speed transition, a bump that would occur when I'm shifting 3407 between speed mode and one of the positioning modes. So I'm going to turn 3114 on. And it also disables the profiler limitations being applied when in speed mode. So we are going to turn that on as well. So I will turn this on like so. Menu 31, parameter 15 is auto resolution. What this is used for is if the user unit ratio is less than 1, right? Or is greater than 1, excuse me. So if the result of dividing 3108 by 3109 is, greater than 1, turning on the parameter will aid in providing more resolution to the speed loop. So let me rephrase myself there. If the ratio is greater than 1, you'd want to turn this on. So the example today, what we're doing is if you look at that, that's 3108. Divided by that, it's less than 1. So we have no need to turn that on. So you'd want to turn this on if the result here was greater than 1. Otherwise, we can leave it off. So I'll go back there and show that it's left off. So that's what I have for you today. Does anybody have any questions? Oh. I believe that's read-only, right? Yeah, that's read-only. Oop. Yeah, you can't adjust that one. Anything else? Anybody have any questions? Looking at the chat here, I don't see anything. So now that we've got the AMC set up, tomorrow we're going to use it. We'll start with speed mode, we'll do homing, and positioning. Okay? Thanks very much for your time today. I appreciate it. And I will see you same time, same station tomorrow. You're welcome.